Logarithmic differentiation, part 1. Logarithmic differentiation makes frequent use of these properties. So you want to make sure that you're able to apply these super quickly. So just like you're able to add 2 plus 3, you want to be able to apply these properties. In general, we're going to go from an expression that looks like this to that. So we're expanding these. So if you're feeling a little stuck or you're not feeling like you can apply these fluently, you might want to get some practice. You might even want to pause, go get some practice, and then come back. Because if you're getting stuck on the logarithmic properties, then some of these problems are going to look a little extra confusing. Another thing to keep in mind is that log base e of x is ln of x. So the natural log of x. So all of these properties here apply to natural logarithms as well. Another thing to keep in mind is that although we have log base b of ab is equal to log base b of a plus log base b of b, if we have the log of a product, we can split those up into separate sums. If you have the log of a sum, that can't be simplified any further. These are the same thing. We cannot split up logs that have sums on the inside of that logarithmic function. This is already simplified. A lot of people try to use like a misinterpreted version of this. So they'll try to split this up like this, but that's not how it works. So make sure you're careful that you're not simplifying things incorrectly. Before we can do logarithmic differentiation, we're going to need to know a couple derivatives of logarithmic functions. So what is the derivative of the natural log of x? We can actually find this out using implicit differentiation, because right now we don't know what the natural log of x is, so if we try to take the derivative with respect to x of both sides, we just end up stuck. So instead, we can try undoing this natural log of x, and the inverse function for natural log of x is e to the x. So we'll exponentiate both sides. So we have e to the y is equal to e to the natural log of x, which means we have e to the y is equal to, well, since e and natural log are inverses, they'll undo each other. So we're left with just x. And now, since we know the derivative of e to the y, or rather e to the something, and we know the derivative of just a variable, we can take the derivative with respect to x of both sides. So we have d dx of e to the y is equal to the derivative with respect to x of x. The derivative with respect to x of e to the y will be, well, the derivative of e to the something is e to the something times the derivative of whatever was inside of that, and the derivative of y is dy dx. So we just used chain rule and implicit differentiation there. And the derivative with respect to x of x is just 1. In order to solve for dy dx, the derivative, we'll need to divide both sides by e to the y. So we have that dy dx is equal to 1 over e to the y. But in this case, the original function was already solved for y, which means that we can substitute whatever y is equal to as a function of x back in for y. So we have 1 over e to the y, which means we have 1 over e to the natural log of x. So we just substituted that back in for y. And again, just like before, our e to the natural log cancels out, and we're left with just 1 over x. So the derivative with respect to x of y, which in this case is the natural log of x, is equal to 1 over x. We can use a similar process to find the derivative with respect to x of log base a of x. And when we do that, we end up that derivative is 1 over x times the natural log of a. And since we've learned so many other types of differentiation, including quotient rule, product rule, and chain rule, we'll also want to keep in mind how the natural log of x interacts with the chain rule. So if we have the derivative with respect to x of the natural log of another function, we'll have to use chain rule. So that will give us, well, the derivative of our outside function natural log will be 1 over whatever is inside of it. So that'll be 1 over u of x. And then we need to multiply by the derivative of whatever is inside of it. So that'll be u prime of x. And frequently, we just write this as u prime of x over u of x. Because as part of logarithmic differentiation, we end up using chain rule with logarithmic functions, specifically natural logarithmic functions, very frequently. So this shortcut is very common. Let's take a look at y is equal to the natural log of the quantity 3x plus 2. Be very careful. This is already simplified. We cannot use any log rules to split this up. But we can try to take the derivative of this. So if I take the derivative of both sides, dy dx will be equal to, well, I have the natural log of something, so I'll have to use a bit of chain rule here. The derivative of natural log of something is 1 over that something, so 1 over 3x plus 2. And then I have to multiply by the derivative of that something by chain rule. The derivative of 3x plus 2 is 3. So dy dx is equal to 3 over 3x plus 2. Now we have y is equal to sine to the 4th power of x. Well, let's rewrite this real quick. So we have y is equal to the natural log of, that's sine of x to the 4th power. And we can actually use the properties of logarithms to continue to rewrite this. So that'll be y is equal to 4 times the natural log of sine of x. So we still have one layer of chain rule, but that's far fewer, well, it's only one fewer, but that can make a big difference than if we looked at this, where we'd have 3 layers of chain rule. So let's take the derivative now. So we have dy dx is equal to, well, this 4 is multiplying the function, so it's going to follow our derivative along. So we have 4 times, our outside function is natural log of x, and we have this sine of x inside of it. So we'll have 1 over sine of x. That's the derivative of that natural log of something, times the derivative of what was inside our logarithmic function, which is a sine of x. The derivative of sine of x is cosine of x. So dy dx is equal to 4 cosine x over sine of x, which is equal to 4 cotangent x.